This is because your heart is constantly putting blood there. When you press it, you squeeze the blood out of those capillaries and veins, but you release the heart, the blood keeps pumping right back into it. So the skin will be white when you press it for like a split second, then you remove it and it immediately turns red, or the natural color. This is an alive person. Now you see this darker purple, let's say on his right side, where it pooled at his on the bottom of where he's lying. You press that with your finger. Remember, there's no heart pumping that blood in there. It'll be white because you're squeezing the blood away, and slowly the color will seep back in. Because there's blood all around, it pools over there, but this heart doesn't immediately push it right there. So it'll seep back in. That's called whitening or blanching. It doesn't go away quickly. So you test it. You see the body. Is there any bluish purple toward the bottom of, let's say, where he's lying? If there's none, okay, then you rinse. Since this starts 20 minutes to 3 hours after death, we know it was less than 3 hours, let's say. Okay, that's number one. Then if we do see it, well, what we do is we start pressing it, and we press it. If the blood where on we see the blood seeps in, then we know this is, blood does not, we press it and the blood slowly seeps in, then we know, okay, this is real livor mortis, this is where the blood is, and we keep on pressing it higher and higher so we can see how long it took for the blood to pool and how much blood pooled. So that's one way of doing it, of telling. This continues until 16 hours after death. At that point, or as time goes on, you press it, the blood congeals in those, wherever you're pressing it. So you press, you're actually not squeezing the blood out. It's too thick. So you press it, you're just going to indent this reddish, or rather bluish purple, livor mortis area. So you press it in, it'll go in, but it won't turn white. So you will not have this blanching. So you can tell, in the beginning, you might see none of the bluish purple. Then you'll see bluish purple only at the bottom. Then get a little bit higher. Then eventually you're not going to see any blue. There's blanching. The lower areas where it pools. Then there's blanching a little bit higher. And eventually there's no blanching at all because the blood has set. The blood has congealed, and you're not going to squeeze it out of the blood vessels that easily by pressing with your finger on it. And this is not something I can teach you. It takes experience with how hard you press it and how to work the time based on the blanching. This depends on the temperature of the body. Like in hotter areas, it'll be a little bit faster. So this is not as clean a way to find the dead body. There's a lot of factors involved. So it's not as easy as the Algor Mortis that we mentioned before, the temperature of the body. This is how the blood pools. So however, this thing, we can tell something interesting. Different patterns on the body can show if the body was moved. Let's say we see the body and blood pooled on its right side, but it's lying on its left side. So what must have happened is the person was killed. The livor mortis set in and made the bluish purple part on his right side, because that's how he was killed. Then the person moved the body onto his left side. So this livor mortis, the livor mortis pattern that we see, can very well tell some interesting facts about what happened after the crime. Then there's rigor mortis. You might have heard the term. That's the stiffness of death. Incidentally, if you want to know where these came from, Algor Mortis is the temperature of death, or the dead body. Livor Mortis is the color of the dead body. Whereas rigor mortis is like the stiffness. It's the stiffness of the muscles. After death, after a certain amount of time, the muscles start to stiffen. And this continues until about 24 hours. And after 24 hours, it's gone after about 36 hours. Then the body muscles they lose their stiffness and they return to the flabbiness that dead bodies often have. So this depends on this. Again, it seems like a very if you know how stiff it is, you can gauge how quickly how long ago the body was killed. But there are factors that make this a little bit harder to determine. If the person exercised before death, then the rigor mortis becomes stiffer faster. If the person is a bodybuilder, then again it might be more. If a person's obese and really not in shape, then you're not going to have that much rigor mortis. You're not going to have that much muscle mass. You're not going to have that much stiffness of the muscles. And it does depend on the temperature. The higher the temperature, the faster the rigor mortis will happen. And the faster it will go away too. One interesting thing is, because the muscles stiffen after death, if you find the body, let's say, with a hand stretched up, then something strange here. That's because the person died in a strange position, and it stiffened there. So again, this can tell a little bit about the position the person was in when they were dead, and that tells a little bit about the reconstruction of how we can reconstruct the crime. We also test the potassium ions in the eye fluid. We take a needle or a syringe, and we suck out the vitreous humor, that's the fluid in the eyeball. We take 2 samples, one, let's say, an hour apart from the other. And we use a formula. The fact is that the amount of potassium ions depends on the rate that potassium ions leak into the eye fluid times the time plus the time that the person died. So in a way, we really want to. So with this, we have these 2 equations that we can use. We test the amount of potassium ions in the first analysis after 1 hour, and that's equal to the rate. We don't know the rate. We do not know this. We have to solve for the rate. And the time of the first analysis that we know, let's say that's the first hour, 1 hour. I don't know, whatever the time might be, 10 o'clock, whatever you're going to put over there. So this we know. We measure the amount of potassium ions. We know the time that we did it. We don't know how fast it goes, and we also don't know the time the potassium leaked into the eyes. That is the time of death. This is what we really, really want to know, the time of the death. So we do this for 1. Then we do this for another, let's say an hour later. So we're going to analyze the amount of potassium there. So we know what this is after we analyze it. We still don't know the rate, but it's the same rate for both same body, it's the same rate for both tests of potassium ions. The body is going to produce this potassium ions in the eye fluid at the same rate. So we don't know the rate. We still don't. We do know the time of the second one. Let's say it's 2 hours later. Let's say it's 12 o'clock. I don't know. So we know the time, and we don't know the time of death. We don't know the time that it began producing this potassium ions into the eye fluid. So we have 2 equations. This is equal to the rate times the time plus the time it began. And the second one, the rate times the time plus the time it began. 2 equations, how many unknowns? Rate and the time it began. 2 equations, 2 unknowns. You can solve this algebraically. So what we do is we subtract, let's say, the second from the first. And that will get us, this will cancel, and it'll get us the delta K plus. That's the change in potassium ion concentration. That's the second minus the first. Remember, we subtract the second from the first. And the time between samples, let's say 2 hours and 1 hour, that'll be 1 hour in between. That's equal to the rate. So no longer is the rate an unknown anymore. The change in concentration divided by the time between the samples is going to be equal to the rate of potassium ion production. Once the rate is known, we can plug this back into the first equation. This we know.